Welcome to the video lecture on parametric equations. In this lecture, we will discuss graphs as a collection of ordered pairs x, y, which may or may not be a function and which are defined by what we call parametric equations. Parametric equations are often used to describe movement along a curve with respect to a variable t, where t may represent time. What we do is we let x be a function of t and y be a function of t, where f and g are two functions whose common domain is some interval I. The collection of points defined by these two functions, where x is f of t and y is g of t, is called a plane curve, and the equations x equals f of t and y equals g of t, where t is in this domain I, these are called parametric equations of the curve. The variable t is called a parameter. When plotting the points for increasing values of t, a direction for the curve is established, and this is called the orientation of the graph. So let's see an example of what some parametric equations might look like and what the graph would look like. We're going to consider the parametric equations x equals 1 minus 2t and y equals 1 plus t, where we're going to let t vary between -1 and 4. We're going to fill out this table to get some points, and then we're going to plot the points over here on our graph. So we're letting x be 1 minus 2t and y be 1 plus t. So the way the parametric equations work is you kind of have this third variable, this third parameter called t, that varies over some interval of values. And what we want to do is let t range over these values in our table and substitute them in to figure out what the x and the y would correspond to. So for example, if t was -1, -2 times -1 would become +2, plus this 1 out front makes this a 3. If we let t be -1 over here for y, we get 1 plus -1, so y would be 0. Now let's let t be 0. 2 times 0 is 0, 1 minus 0 stays 1, 1 plus 0 stays 1. Now let's let t be 1. 2 times 1 is 2, so 1 minus 2 would be -1, and 1 plus 1 would be 2. Let's let t be 2. 2 times 2 is 4, 1 minus 4 is -3, and 1 plus 2 is +3. If t is 3, we get 2 times 3 is 6, 1 minus 6 would be -5, and 1 plus 3 would be 4. And finally, if t is 4, 2 times 4 is 8, 1 minus 8 would be -7, and 1 plus 4 would be 5. Now, when you're graphing parametric equations, you want to be considering the orientation of the graph, which means the direction that the graph would go as your t values increase. So when t is -1, the starting point would be this 3, 0, right here on the x-axis. Then, if t is 1, my next point is 1, 1, right here. If t is +1, then our point is -1, 2, so that would be up here. If t is 2, then I'd be at -3, 3. If t is 3, then I'm at -5, 4. And if t is 4, I'm at -7, 5. And the way we show this orientation is we start at our beginning point and we connect these dots in the direction that we were moving, and sometimes we even draw an arrow. So our orientation is that we're going up and to the left. And notice that as t increased, what happened to the x's? These x's went down, they decreased. And what happened to the y's? The y's went up, so they increased. So this is a fairly basic example of a parametric equation. Let's see another one. Before we do, actually, let me go back. Let's sketch this on the calculator. I forgot that I wanted to show you that. So let me show you how you can sketch parametric equations on your calculator. So let's pull up the calculator. And what we want to do first is change our mode. Normally we're in function mode, occasionally we're in polar mode. For this lesson we want to be in parametric mode. So that's PAR right over here next to function. You want to hit enter and highlight it. And now we're in the right mode, so when you go to y equals, it's not going to look like y equals anymore. It's going to look like x sub 1t equals and y sub 1t equals. So this first pair of x's and y's is going to be your parametric equations. And in our problem, our first x formula there was 1 minus 2t. And when you press this variable button, normally it pops up with an x, but this time it's going to pop up with a t, since that's the parameter that we usually use when we're doing parametric equations. Now if we go to y, we wanted y to be 1 plus t. And before we sketch this, I want to show you the window. So take a look at your window here. And on this window I have some old values put in, so I want to adjust this. How did we want our t's to range? We were told to let t range between -1, so I'm going to let that be my t min, and +4. So that's going to be my t max. And for my t step, let's just change it to 1, since in my table all of those t values went up by 1. And then for my x's, we had some x's that were a little bit smaller than -3. So let me just go ahead and make this -10 to 10 by 1s, and for my y's I'll do -10 to 10, and we can adjust this more if we need to. Keep arrowing down and you'll see that y max in there, and if you needed to you could arrow down again to get that y scale. And now let's hit graph. So here it is. Now something else I want to show you, if you go back to y equals, arrow over to the left of that x sub 1 and see where this cursor is now flashing. Hit enter a few times until the character next to it changes to this little circle with a line after it. And what this is going to do is it's going to show us in an animated sort of video here of what direction this graph goes, because it's going to show us as t changes from -1 to 4 what these points look like. So go ahead and hit graph and you'll see what I mean. So you follow that little circle and it shows you that we started over here on the right and we went up and to the left. So it's a nice way to show that orientation so that you can see in which direction the graph is going. Okay? So on my calculator we got the same graph that we had earlier, and just to remind you, for our t min we used -1, for our t max we used +4, and for our t step we just went by 1s, and then we did our x min and x max -10 to 10 and our y min and y max -10 to 10. Now the last thing I want to show you about this problem is how to eliminate the parameter. This graph right here looks like the equation of a line, and if we eliminate the parameter, which means to get rid of the t, then we will come up with what the equation of this line is in its Cartesian or rectangular form. So let me show you how to do that. Remember that x was 1 minus 2t and y was 1 plus t. So an easy way to eliminate the parameter is to take either one of these two equations, whichever one is easier, and solve it for t. And I can do that pretty easily over here by just subtracting 1. So now we know what t is, and then what I'm going to do is substitute that in over here for the t in the other equation. So this becomes x equals 1 minus 2 times parentheses y minus 1. And now there is no more t showing up here. That's what it means to eliminate the parameter. Let me just simplify this. So we're going to get 1 minus 2y plus a 2. If I add that 2y over to the other side, we get x plus 2y is equal to 3. So this is the equation of this line right here, but it's not the whole line, it's only the line where t ranged between -1 and 4. So you have to be a little bit careful. This is the graph in its rectangular form, but in our parametric form we did have restrictions on what domain we could use. And we'll talk more about that a little bit later. Let's sketch the graph of the parametric equations x equals t cubed and y equals t squared, where t is all real numbers, noting the orientation. So what we're going to do here is we're going to make a graph, and in order to see what our graph is, it's always a good idea to make a table of values. So I'm going to let t vary, and I'm going to find out what x is and y is. And remember here that x is t cubed and y is t squared. Now, since they don't really give us any restrictions on t at all, t can be all real numbers, we can choose whatever we want. So in a problem like this, I usually like to pick a nice selection, a nice variety of t's. So maybe I'll let t be -2, -1, 0, 1, and 2. So I'm using a few negatives, a few positives, and 0. Now x is going to be all of these t's cubed. So -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. And y are all these t's squared. So this would become 4, 1, 0, 1, 4. Now remember, this could continue on this way and this way through more negatives and more positives because t is all real numbers. So I'm not really just starting at this point and stopping at this point, but it will give me an idea of what the shape is going to look like. So when t is -2, I'm supposed to be at -8 for x and +4 for y. And then when t is -1, I'm at -1, 1. When t is 0, I'm at 0, 0. When t is +1, I'm at 1, 1. And when t is 2, I'm at 8, 4. So hopefully you can see the orientation. I'm kind of coming down here, and it's not really a straight line. It's kind of arcing here a little bit, and then it's coming up this way. Sometimes I show that with some arrows like this so that you can kind of see. And because it didn't just start here and stop here, you can continue those arrows and just show that it does keep going. Okay? Now we want to sketch the graph of the parametric equations x equals cosine t minus 2 and y equals sine t plus 3, noting the orientation of the graph. So here's my two parametric equations. And we want to make a graph, so we're going to make a table. And this time, because x and y are in terms of trig functions, the t's that we use probably should be nice angles that we would normally use on our unit circle. So when you're picking these t's, make use of some of those nice angles. And I'm going to start by just, whoops, I don't know what happened there with my pen. Let me clean it up here a little bit. There we go. So I'm going to just start by using my quadrant angles, and then I can always add more if I need more points. So I'm going to start at 0 for t, then I'm going to do pi over 2, and then I'm going to do pi, and then I'm going to do 3 pi over 2, and then I'm going to finish at 2 pi. And we can always add more, like some pi over 4s, or pi over 6s, or pi over 3s, if we feel like we're not getting the full picture. So if x is 0, cosine of 0 is 1, 1 minus 2 is -1. If if t is 0, sine of 0 is 0, 0 plus 3 stays 3. If t is pi over 2, cosine of pi over 2 is 0, 0 minus 2 is -2. And if t is pi over 2, sine of pi over 2 is 1, 1 plus 3 would be 4. Cosine of pi is -1, -1 minus 2 is -3. Sine of pi is 0, 0 plus 3 is 3. Cosine of 3 pi over 2 is 0, 0 minus 2 is -2. Sine of 3 pi over 2 is -1, -1 plus 3 is 2. And 2 pi, cosine of 2 pi is 1, 1 minus 2 is -1. Sine of 2 pi is 0, 0 plus 3 is 3. So let's sketch these points. When t is 0, x is -1 and y is 3. At pi over 2, x is -2 and y is 4. At pi, x is -3 and y is 3. At 3 pi over 2, x is -2 and y is 2. and at 2 pi, x is -1 and y is 3, so that's this same dot again. So imagine we started at this dot, then we went up to this one, then we went to this one, then we came around, and we looped back around again. So what we ended up with here is a circle. So let's see what happens if we were to graph this on our calculator. So if we go to our y equals, we're going to clear these out, and I'm going to type in cosine of t, close the parentheses on the t, minus 2, and then we're going to type in sine of t, close the parentheses on the t, plus 3. Make sure you're in radian mode. You want to make sure you're in radian mode. And when we go to window, remember how we used our t's here? We used t's that were angles. We want to do that here as well, just to make these values come out nice. So I'm going to let my tmin be 0, and I'm going to let my tmax be 2 pi. So 2, and then I'm going to click pi. Now, if we do the same t step that we used here, how much did these t's go up by each time? They went up by pi over 2, or 90 degrees each time. So I'm going to show you what happens if we use a t step of pi divided by 2. And I'll leave my x-min and my x's and my y's from -10 to 10. So let's go ahead and graph, and let's see what we get. Now this looks sort of like a circle, but it's kind of pointy on the edges. And that's because we're only looking at 4 values, those 4 corner points. So it's not enough for the calculator to get some real accuracy. So if you go back to your window and adjust this t-step to something a little bit smaller. So let's say instead of going by pi over 2's each time, let's go by pi over 4's each time. So let's change our t-step to pi divided by 4. And now hit graph, and it looks a little bit more rounded. If you go back to window and you change that t-step to something even smaller, like pi divided by 12, or whatever you want to pick, it doesn't really matter. The smaller you make that t-step, the more accurate the graph is going to get, and the more circular shape it's going to have. So you do have to be careful, especially on your calculator, that you are looking at your graph correctly and using the right t-steps. Okay, let's take a look at the next example. Each of the following sets of parametric equations have the same rectangular form but different graphs. Sketch the graph of each and note the restrictions and the orientation. So this first example has parametric equations x equals to t and y equals to 1 minus t. So if we wanted to sketch a graph of this, we would want to make a table of values, and we're going to let t range between some choices, and I might just use my standard choices of -2, -1, 0, 1, and 2. And x is exactly what t is. So x is going to be -2, -1, 0, 1, and 2. So y is 1 minus t, so 1 minus -2 becomes 3, 1 minus -1 is 2, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 2 is -1. So let's plot some of these points. When t is -2, x is -2, and y is 3. So that would be this dot right here. When t is -1, x is -1, and y is 2. When t is 0, x is 0 and y is 1. When t is 1, x is 1 and y is 0. And when t is 2, x is 2 and y is -1. So these points are kind of going down in this direction. So your orientation would be to go down like this. Now, is there any restrictions on what x and y could be? In other words, t can be anything because we don't have any restriction on how t is defined. So since x is also t and there's no restrictions on t, then there's no restrictions on x. And what that means is that the domain for x would be all reals. X can be anything. Now how about for y? Can y take on any value? Well, look at the pattern here. If we let t become more negative, then these y's are going to continue to get bigger going this way. And if we let t become larger, then these y's are going to continue to get smaller going this way. So there's also no restrictions on y, which means the range for the y's is going to be all reals as well. So this is going to continue all the way down like that and come from up above like that. It's going to continue all the way. So our orientation would be in this direction. Now let's eliminate the parameter to see what this would become. Since x is exactly t, then I can just replace this t with an x. So my parameter goes away and I just get the equation 1 minus x. So that's this entire line going down. Okay, now let's take a look at the example x equals 1 minus t squared and y equals t squared. So we're going to make our chart again. We're going to pick some choices for t and figure out what x and y are. And I'm just going to use -2, -1, 0, 1, and 2 again for my t's. If t is -2, t squared would become 4, and 1 minus 4 would be -3. Let me just go ahead and do all my x's at once using the same formula. So if t is -1, squaring that becomes +1, 1 minus 1 is 0. If t is 0, then 1 minus 0 is going to stay 1. If t is 1, 1 minus 1 becomes 0. If t is 2, 1 minus 4 is -3. Now let's do y. Y is exactly this t value squared. So -2 quantity squared is 4, -1 squared is 1, 0 squared is 0, 1, and 4. Now let's talk about our graph. If we draw this, when t is -2, x is -3, and y is 4. So that would be way up here. When t is -1, x is 0 and y is 1. When t is 0, x is 1 and y is 0. When t is 1, x is 0 and y is 1. So we're back to here again. And when t is 2, x is -3 and y is 4. So notice what happens. We got these same 3 dots. We went down, hit this point, and then we bounced back around and came back. So for our orientation, we kind of go down and then we went back up again. So let's talk about the restrictions. Look at what happens to your y's for a moment. Since y is defined to be t squared, what do you notice about all these y values? Since t squared is equal to y, and t squared is always greater than or equal to 0, in other words, it's always 0 or something positive, then that means y has to be always greater than or equal to 0 as well. That's why all these y coordinates are above the x-axis. So our range for y is going to be from 0 on up. We're never going to get any y values down here below the x-axis. Now look at the x's. Notice what happened. As we went down, if you look at the rule for x, when t became 0, when t became 0, we got x is equal to 1. That was this dot. And when t became 1 or -1, these became 0. And that was the lowest that this point got on that x-axis, or that y-axis. The height was 0. So this was our lowest point, and then it bounced back up again. So what's this, the x that corresponds to? That corresponds to an x value of 1, and I'm not going to get any x's beyond that, because as we look at the rule for 1 minus t squared, the largest that this is going to get is at 1, because as t goes to 0, that's the biggest that this value can get, and if you pick any other t and you square it, you're just taking that away from 1, which is going to make this get smaller. So the largest that this gets is x equals to 1, and as t goes to infinity or even minus infinity, then that's going to get 1 minus something very, very, very large. So that's going to go to minus infinity in this direction. So you can see for our domain, we're going to go all the way to the left here as these points continue, but we're not going to go any farther than this 1. So for our domain, the restriction would be minus infinity up to 1. So we hit all of these negative x's, but we don't go beyond 1 on that x-axis. So our domain for the x's is minus infinity to 1, and our range for the y's was 0 to infinity. Now let's eliminate our parameter. Since y is defined to be t squared, we can replace this t squared with y, and we get x equals 1 minus y. And if you were to solve that for y, we would get x minus 1 is equal to negative y, and if I divide through by a negative 1, the signs change, and if we just switch the order around, we get y equals 1 minus x, which is exactly the same rule that we got up here, but it was a slightly different looking graph because this one went all the way down and all the way up, and this one just hits at 1, 0 and then bounces back up again. So this has a slightly different look to it because we have a slightly different domain and range. This time we have restrictions. Now let's take a look at this parametric equation. X equals cosine squared t and y is equal to sine squared t. So if we wanted to make a graph of this, we would want to pick some t's and find out what our x's and our y's are. And because we're dealing with cosines and sines again, we're going to want to make sure that the t's that we pick are nice angles. And you can use your quadrant angles, you can use any of those nice angles that we have on our unit circle. So I'm going to start with my quadrant angles: 0, pi over 2, pi, 3 pi over 2, and then you could go back to 2 pi as well. It should give you the same thing as 0. And then if you want, you could try, say, pi over 4 or pi over 6, something like that. And I'll just show you a couple of those. So let's start with the x's. If x is 0, if t is 0, then cosine of 0 is 1, and that squared is going to stay 1. If I plug in pi over 2, cosine of pi over 2 is 0, and that squared stays 0. Cosine of pi is negative 1, and that squared becomes positive 1. Cosine of 3 pi over 2 is 0, and that squared stays 0. Cosine of 2 pi is 1, and that squared stays 1. So it looks like we're just bouncing back and forth, but if we look at some of these smaller angles, like pi over 4, cosine of pi over 4 is root 2 over 2, and if you square that, that becomes 2/4 or 1/2. If I look at pi over 6, cosine of pi over 6 is root 3 over 2, so if I square that, that gives me 3 on top and 4 on the bottom, so 3/4. Now let's do our y values. So if we plug in 0 for t, sine of 0 is 0, and that squared is going to stay 0. Sine of pi over 2 is 1, 1 squared is 1. Sine of pi is 0, so this will be 0. Sine of 3 pi over 2 is negative 1, and that squared becomes positive 1. Sine of 2 pi is 0, so this is going to stay 0. Sine of pi over 4 is that root 2 over 2, and when you square it, you're going to get that 1/2 again. And sine of pi over 6 is a half, and when you square that, you're going to get 1/4. So if we plot these points, when t is 0, we get 1, 0, which is right here. When t is pi over 2, we get 0, 1, which is right here. Then we're back to 1, 0, then we're back to 0, 1, then we're back to 1, 0, then we're back to 0, 1. Some of these intermediate points, this pi over 4, which would have occurred right in between these two, right in here, we would have started at this 1, 0, which was right here, and then we would have hit pi over 4, which was at 1/2, 1/2. So that would have been right here. And then we would have gone to pi over 2, which is this 0, 1. So it's right in line with these 2 points. And same for pi over 6. 3/4 and 1/4 would have been right here. So these 2 points, even though they're not 0, 1 and 1, 0, they're right in this line segment between. So what you'll notice is that on this problem, what we have is our graph starts at 1, 0 over here, and then it goes up, and then it goes back again. So we start down here, we go up, and then down, and then up, and down, and we bounce back and forth between 0, 1, and 1, 0. So what are the restrictions then? You can see that from this graph. What's our domain for x? What x's do we actually use here? The only x's we use are from 0 to 1. And the only y's we use are these y's right here, which is also 0 to 1. So a much different picture than the other two because we have these restricted domains. Now let's eliminate our parameter. And in order to do this, you want to notice that x is cosine squared and y is sine squared. And we know that cosine squared t plus sine squared t is that Pythagorean identity, so that has to equal 1. And cosine squared is just x, and sine squared is just y. So this just becomes y equals 1 minus x. So the same rectangular or Cartesian equation for all three of these examples, but very different looking graphs because of the way that we have parameterized them. So how you choose your parameterization determines what your graph is going to look like. So now what we're going to do is come up with two different ways to parameterize some equations. So we have y equals x squared minus 1, and we want to figure out a way to write parametric equations for this in two different ways. So a really simple way is just to let your x become t, and then you're going to rewrite this equation by substituting in a t where that x was. So this would become t squared minus 1. So that's the most basic way to create parametric equations. Now, how could you create another parametrization? Well, you would have to choose your x differently. So instead of just letting x be t, you could let x be t plus 1, for example. And then if we substitute that in for this x, this would become t plus 1 quantity squared minus 1. And if you simplify that, that's t squared plus 2t plus 1 minus 1. The 1's cancel, so y equals t squared plus 2t. So this is a second way that you could make parametric equations. Now you just want to make sure that when you do your parametric equations that you're maintaining the correct domain. If we want the full graph of y equals x squared minus 1, that's a quadratic parabola, and x is allowed to be anything at all, minus infinity up to positive infinity. And if we let our x be equal to t, that maintains that restriction, because t can be anything, therefore x can be anything. And likewise with this restriction here, t can be anything, so x can be anything. So you just want to make sure that you're not restricting your domain at all by the way that you choose your parameterization. Let's try another example. If I have y equals to square root of x, again, a really simple way to create parametric equations is just to let your x be the t, and therefore the y becomes square root of t. So really simple. Now to get a second parametric set of equations, we could just choose x to be something different. And if I let x be, say, let's try 4t. I'm going to use 4 because I know I'm going to end up here taking the square root. So I'm going to substitute in 4t right where that x is. And because it's a nice perfect square, it reduces to 2 square root of t. So you could have these two sets of parametric equations. Okay? All right, the next example. Find parametric equations for an object that moves along the ellipse x squared over 4 plus y squared over 9 equals to 1 with the motion described. So this first one, we want our motion to begin at 2, 0 and be counterclockwise and require 2 pi seconds for a complete revolution. So we want our graph to start at 2, 0 and go counterclockwise and complete 1 full revolution around in 2 pi seconds. So we want it to look something like this. And this wouldn't have the shape of a circle, it would be that ellipse shape. So what we would want to do is figure out what we're going to let our x be in terms of t, and what we're going to let our y be in terms of t. And so far what we want to know is we want this to start at 2, 0. So we want x to be 2, and we want y to be 0 at t equals 0, at the start. So that's one restriction that we need to have. The other thing that we need to maintain is that whatever we let our x and our y be, it needs to satisfy this elliptical equation. So think about how that could possibly happen. And this is kind of a tricky one. It might not be something you would normally think to do on your own, but once you see an example like this, it's a pretty common type of problem. So here's kind of the trick that we're going to use. We know that by the Pythagorean identity, cosine squared t plus sine squared t is equal to 1. We're going to use that fact to try and replicate this sort of elliptical equation. So what I'm going to do is I'm going to manipulate this a little bit, and what I can do is give a coefficient to this cosine squared t and make it 4 over 4. So I'm still keeping this outer coefficient of 1, but I'm making it look a little bit more similar to this fraction here, where the x would be the square root of this numerator. So we could possibly let x be 2 cosine t. And then, to make this part match and get a 9 in the bottom, I'd have to have a 9 on the top to make this Pythagorean identity still be true. Because remember, we want these 4's to cancel to give a 1, and we want these 9's to cancel to give a 1, so that we end up with that basic cosine squared plus sine squared equals to 1. We want that to still be true. But if I choose to set up my equation so it looks kind of like this, then I could let my y be the square root of this numerator. In other words, y could be 3 sine t. So let's try letting x be 2 cosine t and y being 3 sine t. Now, I'm not sure if it's going to satisfy our initial condition here, as well as our other requirements about how fast it completes a revolution. We're going to have to see if this really does work. So here's what we're going to check. We're going to make a table of values, and we're going to let our t range from 0 up to 2 pi. And I'm just going to use those nice quadrant angles again. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And from this span of 0 to 2 pi, we want to be able to complete our full revolution. So if t is 0, and I plug in 0 for x, then cosine of 0 is 1, and 2 times 1 is going to be 2. If I let t be 0 for y, for this t in the y, sine of 0 is 0, 3 times 0 is 0. And that's exactly what we wanted. We wanted to start at 2, 0. So far, our graph is starting right here. So that's good news. Now if we let t be pi over 2, cosine of pi over 2 goes to 0, but sine of pi over 2 goes to 1, so this would become 3 times 1, or 3. So in our next t value, we're at the point 0, 3, which would be right up here. So we're kind of moving in this direction, which is counterclockwise. So far that looks pretty good as well. Now let's let t be pi. Cosine of pi is -1 times 2, so this is going to be -2. Sine of pi is 0. So now we're at -2, 0, which would be over here. So again, we're continuing along in this direction. So that's still going counterclockwise. If t is 3 pi over 2, cosine of that is 0. And sine of 3 pi over 2 is -1 times 3, so this would be -3. So that's at 0, -3 down here. So we're continuing along this way. And if t is 2 pi, cosine of 2 pi is 1, times 2 is 2, sine of 2 pi is 0. So now we're back to 2, 0. So we went one full revolution around this ellipse, and we did it in the span of 2 pi seconds. So that's kind of like our period. We did one revolution in a period of 2 pi. If I kept going and I did another period of 2 pi, so if I continued my table and went from 2 pi up to 4 pi, I would just continue to loop around this ellipse. So this is how we would need to parameterize our ellipse to end up with this particular rectangular equation and have the following motion. Okay, so now what we're going to do is modify this a little bit. So we still want the motion to begin at 2, 0. We still want it to be counterclockwise, but this time I want it to complete one revolution in only 1 second. So instead of taking 2 pi seconds, so from t ranging from 0 to 2 pi, going through that ellipse, this time I want the ellipse to go from 0 to 1 second. So we would need our table to go from 0 all the way up to 1 and finish that whole loop around. So what are we going to have to change in order for that to happen? Well, think about what this 1 second sort of corresponds to. And I mentioned it up here when I referred to this 2 pi. We completed one revolution going around this ellipse in 2 pi seconds. If I had gone from 2 pi to 4 pi, then I would have completed another revolution. So this 2 pi up here is kind of like the period. So if we want to complete a revolution in 1 second, then we need to change the period to equal 1 instead of letting the period be 2 pi. So how do you change the period if you are talking about trig functions? Remember that the number in front of your t here is where that period comes from. If you remember our lecture on transformation, sometimes we called that coefficient in front of our x or our angle b. So the b is what affects your horizontal stretch or compression, which affects your period. And there was a formula for it. Your new period was equal to 2 pi divided by whatever that b was equal to. So if we want our new period to be 1, what does b have to equal? If I multiply that b across to the other side, I need that coefficient b to equal 2 pi. So all we have to do to change this scenario is we're still going to let x be 2 cosine, but I want this coefficient in front of my t to be a 2 pi t. And I'm going to let my y be 3 times sine of 2 pi t. So I'm just changing this little coefficient in front of the t to change my period. So let's see if this really works. If I let t range from 0 to 1, let's pick some nice fractions that we could use to get additional points. Let's let t be 0, a quarter, a half, 3/4, and 1. So if I let t be 0, 2 pi times 0 stays 0, cosine of 0 is 1, 1 times 2 is 2. If I let t be 0 down here, I get sine of 0, which stays 0. So that first point is still at 2, 0, which is what we wanted. We wanted it to start at 2, 0. Now let's plug in 1/4. 2 pi times 1/4 is the same as pi over 2, and cosine of pi over 2 is 0. Sine of pi over 2 becomes 1, and 3 times 1 is 3. So now we're at the point 0, 3, and we're going in this counterclockwise direction. If I let t be a half, 2 pi times a half is just pi. Cosine of pi is -1, times 2 is -2. Sine of 2 pi times a half is sine of pi, and that's 0. So that point is now over here, and again, we're moving in that counterclockwise direction. If I plug in 3/4, 2 pi times 3/4 is 3 pi over 2, cosine of that is 0. Sine of that is -1 times 3, so this is -3. So now we're down here at the bottom, and if I plug in 1, cosine of 2 pi is 1, times 2 is 2, sine of 2 pi is 0. So now we're back to our start. So we again looped through our ellipse, but this time we did it from 0 to 1. So we completed one full revolution in 1 second. Okay, one last modification. This time we want our motion to begin at 0, 3. We want it to be clockwise, and we want it to take 1 second for a complete revolution. So the fact that we want our 1 second for a complete revolution means we're going to use that same b that we used in the last example. So we're going to need a 2 pi times our t's again. But the fact that we want it to start at 0, 3 means we are going to have to make a few changes. Let's think about what it's going to take to make this work. We want our table to start at 0 for x and 3 for y when t is 0. If we use what we started with for these last two examples and we let x be 2 cosine 2 pi t again, that's not going to work, because when I plug in 0, that's going to give me 2, and when I plug in 0 for this t, that's going to give me that 0. So we're not at the right starting point. But what I could change in order for x to be 0 is, instead of letting x be the cosine function, we could let x be the sine function. So I'm going to keep that coefficient of 2 out front, but I'm going to let it have sine 2 pi t, and I'm going to change the y to a 3 cosine 2 pi t. So really all I did was I switched these two functions. Why is that going to work? Well, if I let t be 0, sine of 0 is now 0, and cosine of 0 is 1. 1 times 3 is 3. So that does give me the right starting point by just switching the two trig functions around. And it still maintains my elliptical equation. It's just that I swapped up here, and I chose to call this one sine squared and this one cosine squared. And you still get sine squared plus cosine squared equals 1. So that's still true, but we just made a different choice. We let x be sine and y be cosine instead of the other way around. Okay, let's see if the other restrictions here that we wanted are still going to be maintained. Let's let t be 1/4, 1/2, 3/4, and 1. Now if t is 1/4, 2 pi times a fourth reduces to pi over 2. Sine of pi over 2 is 1, and 1 times 2 is 2. 2 pi times a fourth is pi over 2. Cosine of pi over 2 is 0. So on my graph, we started at 0, 3, which was up here, and now when t was a fourth, we moved to 2, 0, which is here. So we moved in this direction, which is clockwise. So that restriction is also correct. So we've got everything going for us so far. If I let t be a half, 2 pi times a half is pi, sine of pi is 0. Cosine of pi is -1 times 3 makes this -3. So 0, -3 would be down here, and we're moving again in this clockwise direction. If t is 3/4, 2 pi times 3/4 is 3 pi over 2. Sine of 3 pi over 2 is -1, so this becomes -2. Cosine of 3 pi over 2 is 0. So that's -2, 0 over here. And finally, if t is 1, sine of 2 pi is back to 0 again, and cosine of 2 pi is 1. 1 times 3 is 3, so we're back to our starting point. So we made one full revolution in 1 second. So all three restrictions are maintained. Oops, we have an extra page here. Okay, let's go ahead and look at the next example. Here we want to write a rectangular equation for the following parametric equation. We have x equals h plus a secant theta, and y equals k plus b tangent theta, where theta is the parameter. So instead of using t's like we normally do, this time we're using thetas for the parameter. So don't let that confuse you. So we're letting h be defined by this parametric equation, and y is k plus b, tangent of theta. So what could we do to try and get rid of the thetas here and turn this into an equation that only uses x's and y's? That's what it means when it says write a rectangular equation. So what we're going to do is we're going to try to isolate these thetas as much as we can to see if we can get rid of them. So here's what we're going to do. To isolate this secant theta, let's move the h over to the other side. So this becomes x minus h equals a secant theta. And then I could divide both sides by a. So we have x minus h over a equals secant theta. Now let's do something similar for this one. I'm going to subtract k, and then I'm going to divide by b. So I'm trying to isolate that tangent as much as I can. Now, we've been using some of our Pythagorean identities, and you should see that since we have a secant and a tangent, there is potential for using a Pythagorean identity that involves secants and tangents. And this is one that you should memorize. Back when we talked about our identities, tangent squared plus 1 is equal to secant squared. So if we wanted to use that, I need to get some squares involved here. So let's square both sides. So this would become secant squared, and this would be x minus h squared over a squared. And if I square both sides here, I'll get y minus k quantity squared over b squared equals tangent squared theta. So if this identity is true, tan squared theta plus 1 equals secant squared theta, and we know that it is true, let's substitute this in for tangent squared. And let's substitute this in for secant squared. And all I'm going to do now is subtract this whole quantity right here over to the other side and get the 1 by itself. Now this should look slightly familiar to you when you talk about conic sections. This is a hyperbola. It's a hyperbola that's been shifted so that it's centered at h comma k, and it's got vertices at plus or minus a, and you can draw a picture of it if you knew what the h, the k, the a, and the b were. So here is what we end up with. If we define our parametric equations in this way, right here and here, what you end up with when you graph it is a hyperbola. One of the most important applications of parametric equations is in the idea of projectile motion and simulated motion using time as a parameter. So consider a projectile being launched at a height h feet above the ground and at an angle theta to the horizontal. So you might have some object that's h feet off the ground and being shot up into the air like this, where if we considered this horizontal out here, this angle is our theta, and it's going to be launched with some initial speed called v sub 0, and that would be feet per second. The path of this projectile is modeled by these two parametric equations. X is equal to v sub 0 cosine theta times t, and y equals negative 16t squared plus v sub 0 sine theta t plus h. Now where are these coming from? Well, x is measuring our distance in the horizontal direction. So you want to keep that in mind. This is going to be our speed in the horizontal direction. And the reason for that, if we kind of zoom in here a little bit on this region right here, this has an initial velocity sort of shooting our projectile up at this angle. And if we drop a perpendicular down and call this angle theta, if I wanted to know the component of that velocity that's just in the x direction, we could call this x, and using a little bit of trigonometry, cosine of that theta has to be the adjacent side, which is what we're calling x, over that hypotenuse, which is our v sub 0. And if we multiply that v sub 0 over to the other side, then what this is telling us is that our horizontal component to our velocity is v sub 0 cosine theta. So this is your speed or your rate in the horizontal direction, and when we multiply that by time, we get our distance. Now the component in the y direction is a little bit more complicated. This is our speed in the vertical direction. By the same reasoning, we would set up a y right here and call this sine of theta equals y over v sub 0, cross multiply, and so the component of the velocity in the y direction, just in the vertical direction, would be v sub 0 sine theta. But we also have gravity acting on this object, helping to pull this projectile back down to the ground. And that's where this negative 16 comes from. It's actually negative 1/2 g. And if we're using feet per second as our units, g is 32 feet per second squared. So half of that is 16. So that's where it comes from. And then we also have our initial height off the ground having a role in this as well. So the x is your distance in the horizontal direction, your y is your distance in the vertical direction. So suppose that Jim hit a golf ball with an initial velocity of 150 feet per second at an angle of 30 degrees to the horizontal. Find parametric equations that describe the position of the ball as a function of time. So his x position would be, according to this formula, his initial velocity, which is this 150, times cosine of theta, and our theta is this 30 degrees, times t. Now cosine of 30 degrees is the same as cosine of pi over 6, and pi over 6 is square root of 3 over 2. So this becomes a root 3 over 2, and when you multiply that by 150, 2 goes into 150 75 times, so this is 75 root 3 times t is equal to x. So that will give us the horizontal distance that this ball travels from ground. So it's leaving the ground, flying through the air, and eventually is going to hit the ground again. And this is that 30-degree angle. So we're talking about how much the ball travels horizontally with this formula right here. Now how much does the ball travel vertically? That's this other parametric equation, the one for y. So y is going to be minus 16t squared plus the initial velocity, which is 150, times the sine of 30 degrees times t, plus our initial height. And since he's hitting the golf ball from the ground, our initial height is 0. Now sine of 30 degrees is 1/2. So 150 times 1/2 is 75 times that t. So our y parametric equation becomes negative 16t squared plus 75t. Now we want to use these to figure out how long is the ball in the air. So think about what it means if the ball is going to eventually come back down to the ground. We want to know how long it's in the air, so the time from here to here. Well, we know when it started, that's time 0, so we want to find out the time when it hits the ground. And what's true if you're hitting the ground? Your height is 0. Now, is that your horizontal height that we're talking about, or is that our vertical height? Well, if we want the ball to hit the ground, we're talking about its vertical height should be 0, back to the ground level. So in order to solve this, we want our vertical height, which is what we're calling our y, to be 0. So I'm just going to substitute in a 0 for y, and we're going to solve this equation. And that should tell me the time it takes to get back to the ground. Fortunately for us, this one factors. I can pull out a t, and I get negative 16t plus 75. If I set this factor to 0, we get time 0. We already knew that the ball was on the ground initially, so that's what that means. If we set this one to 0, we get negative 16t plus 75 equals 0, and if we subtract that 75 over, divide by negative 16, that on your calculator turns out to be 4.6875. And this is a time in seconds. Our units here were seconds. So it takes the ball 4.68 -0.6875 seconds to come back down to the ground. Okay? All right, next question. When is the ball at its maximum height? And determine the maximum height of the ball. So if we want to know when it's at its maximum height, we're talking about this point right here. There's several ways that you can think about this. One way is to recognize that this y formula that we have representing our vertical position is just a quadratic. And because that t-squared coefficient is negative, it's a quadratic that points down. And if it's going to point down, then it has to have a maximum. And where does its maximum have to be? It has to be at the vertex. So one way to solve this problem would be to find the vertex of this quadratic, -16 t squared plus 75t. And we have a formula for that. To find your vertex, you use minus b over 2a. And this is normally what our x coordinate would be, but in this problem we're not using x's, we're using t's. So this is going to tell me the time when I reach my maximum. So let's figure it out. If I plug in b here is this 75, and I want to divide that by 2 times a, and a is that -16. So this is -75 over -32, and that reduces to 2.34375 seconds. Now what's another way I could have guessed that that was the answer? Look at the picture here. This we're saying is this 2.34375 seconds. It should be exactly halfway in between the 2 times where it was 0. And if we know that it hits the ground at 4.6875 seconds, then halfway between that, it should have been at its peak. And exactly half of 4.6875 is 2.34375. So you could have figured out that time using half of our total t. Now, have we answered our question? We've answered part of it. We've answered the when part. We just figured out when it's at its maximum height, at about 2 seconds. Now let's find its actual maximum height. So to figure that out, we want to know how high we actually went. That's a vertical height, so we want to be using this y formula. We know the t when we're there, so all we're going to have to do is plug in t into this formula, and that should tell me my y. So we're going to use y equals -16 times this 2.34 number squared plus 75 times 2.34375. And when you plug that in your calculator, it's approximately 87.89, and this would be feet. So there's our maximum height, and this was our time. Okay? The last part of the question here is to determine the distance that the ball traveled. So again, the question is, are we talking about vertical distance or horizontal distance? And the way the question is implied is, how far did the ball travel? So that would mean this horizontal distance going across. So we want to know that distance there, which means we need to be using our x formula this time, because that's a horizontal direction. So what we're going to do to figure out how far the ball traveled is use x equals 75 square root of 3 times t. And do we know the time it took for the ball to travel this whole distance? Yes, it was this 4.6875. So that's what we're going to use for t. So 75 root 3 times 4.6875. And when you punch that in your calculator, you get approximately 608.92, and this is feet again, but this time it's in our horizontal direction. So this would be the horizontal distance traveled by the ball. Okay, to finish up, we're just going to graph this motion on our calculator. So if we pull up the calculator, first we're going to type in our equations, and remember our x equation was 75 square root of 3 parentheses times t, and our y equation was negative 16 t squared plus 75t. Now to make this motion become a little bit more animated, so it looks like the ball actually flying through the air, I'm going to change the style of my graph over here. So move your cursor all the way to the left of x1, hit enter a couple times until you see a little circle with a tail following it. And that's going to be our animation, and I'll show you what that looks like in a minute. But before we graph, we need to set up our window. So let's go to our window, and we're going to want to adjust our t's here a little bit. Let's let our t start at 0. And what was our maximum time that we had? Remember, the ball hit the ground at that 4.6875 seconds. So we just want our t max to be something slightly bigger than that. So let's just go to 5. And to show our animation, let's pick a t-step that's kind of small so we can see the animation and it doesn't go by too quickly. If you make your t-step too big, then the ball will fly through the air really fast and we won't be able to see it very well. Now let's adjust our x's. Remember, x was that horizontal distance, so it's not going to start anything negative, so let's let our x-min be 0. But our x max, what was that horizontal distance that the ball traveled? It was that 608 number, so we need something a little bigger than that. So let's try 650. And I'll make my scale go by 50s. And then for my y's, these were the vertical distances. So just to give myself a little bit of room, you could start this at 0, that's totally fine. But I'm going to actually leave this y-min at negative 10 just so we can see a little bit of space here. And I'm going to boost my y max because remember my maximum height of my golf ball was that 87.89. So let's make this go up to, say, 100 so we can see that maximum height. And I'll change my y scale to 10s. And now we hit graph. And here's our golf ball flying through the air, reaches its maximum height, and then it comes back down and hits the ground. Okay? All right, that concludes our lecture on parametric equations. Good luck.